This continues the lectures on Galilean relativity. We now begin to take a look at two-dimensional examples. For two-dimensional examples, when examining, for example, the vector transform here describing velocity vectors, we will ultimately end up with a vector triangle. As you'll discover, that's usually the hardest part about setting up and solving problems two-dimensionally with Galilean relativity, and that is visualizing the velocity transform triangle. So then therefore, what I'm going to do is I'm going to divide up these two-dimensional situations into two parts. We're going to take a look at, first of all, situations where the velocity vectors form a right triangle. This will then make the math relatively easy. And then a little bit later on, we'll take a look at the two-dimensional cases where the vector triangle is not a right triangle. Well, let's go ahead and begin with some right triangle situations. You are already intuitively familiar with how these situations are going to work. Let's take a look at the first of two examples involving right triangles. Okay, so the first example is as follows. A current moves downstream at a speed of 2 meters per second with respect to the shore. A boat is capable of moving with respect to the water at a speed of 3 meters per second. In part A of the problem, the boat is pointed directly across the stream. At what speed and in what direction does the boat move relative to the shore? So let's go ahead and begin to set up part A by first of all identifying everything. Okay, as I've already mentioned, because we're dealing with this topic when talking about motion near the surface of the Earth, this then means automatically that the surface of the Earth becomes the stationary reference frame. So then therefore that's the shore in the context of this example. Okay, then let's begin to picture a top view of the stream like so. So let's say that here are the opposite shores like so, and let's say that the stream is moving in this direction relative to the shore with a speed of 2 meters per second. So it says that the current moves downstream at a speed of 2 meters per second. Which of the three velocity vectors is that? Well, the stream always represents the moving reference frame, and in this case, the boat represents the object. Here's how you could identify which one is which. The object is always the thing that is being described with respect to two other things. So in this example, the boat is being described with respect to the shore, and it's being described with respect to the water. Therefore, the boat automatically becomes the object, and then therefore the moving reference frame O prime, that's the river, that's the stream. If we wanted to, I suppose, we can describe the velocity of the stream relative to the boat, but frankly, we don't care. In this case, we're only concerned with the velocity of the object, that is the boat, with respect to the two different reference frames. So then therefore, O prime is the current, and the object is the boat. This then means that this velocity vector here is u equal to 2 meters per second. This is describing the velocity of the current, O prime, with respect to the shore, O. Okay, and then in the second sentence of the problem, it says that the boat is capable of moving with respect to the water at a speed of 3 meters per second. This is describing the magnitude of one of the other velocity vectors. Specifically, it's describing the speed of the boat, the object, with respect to the water. That is with respect to the current. That's the O prime reference frame. So the magnitude of the V prime vector is given to us, then therefore, as 3 meters per second. Okay, now let's examine part A of the problem. You're already familiar intuitively with how this is going to work. It says that the boat is pointed directly across the stream. So imagine that the boat is pointed like so. So relative to the stream, relative to the current, the boat moves in this direction. However, the current is moving downstream with respect to the shore. So then therefore, into which quadrant on my diagram is the velocity of the boat with respect to the shore? If you're saying the first quadrant, you're correct. In other words, the boat with respect to the shore is going to move like this. What you just did is v equals v prime plus u. Here's how the vectors add together. We have the velocity of the boat with respect to the water, v prime, plus the velocity of the water with respect to the shore, u. That then equals the velocity of the boat with respect to the shore, v. And we have here a right triangle for simplicity in this example. The magnitude of this side of the triangle is what's given earlier in the problem as 3 meters per second. So then therefore, in part A of the problem, basically what we're asked to find are the details of this velocity vector v. I'm going to find its magnitude. We'll just do so by using Pythagorean theorem here on the diagram, and then I'm going to use a little bit of basic trick in order to find an angle. It does say find a direction. Let's just go ahead and define an angle on the diagram, call it theta, and then in just a few moments I'm going to solve for it. Well, let's go ahead and use Pythagorean theorem now to figure out what the speed v is. That is the speed of the boat with respect to the shore. So from this triangle, we're going to have u squared plus v prime squared is equal to v squared. So just plug in. So I'm going to ultimately have the square root here of, first of all, 2 squared, so 4, plus 3 squared, which is 9. Ultimately, we're taking the square root of 13 here, and the speed of the boat with respect to the shore is 3.6 meters per second. Okay, then we'll just use a little bit of tangent here in order to find the angle theta on my diagram. Notice that the tangent of theta is equal to the opposite side here, u, divided by the adjacent side here, v prime. So then therefore we're going to have the inverse tangent of 2/3 as that angle. Let me go ahead and calculate it here on my calculator in degree mode. And when I do, it comes out to be about 34 degrees. Like so. So once again, picture the problem in the following way. We have the velocity of the boat with respect to the water, plus the velocity of the water with respect to the shore. That then gives you the velocity of the boat with respect to the shore, like so. Okay, now there's a part B to the problem here. I have to show it on my screen. In part B of the problem, it says, in which direction should the boat be pointed such that it moves perpendicular to the stream with respect to the shore? So it's once again going to form a right triangle associated with the velocity transformation equation, but it's a different situation than we saw in part A. So here's how we begin to diagram out part B. Okay, once again, here are the two shorelines like so. And then right here is the velocity of the current with respect to the shore. But now what we want to do is the following. Imagine taking the boat like so, and then what we want to have the boat do is move in this direction relative to the shore. So then therefore, in which quadrant on my diagram should I point the boat such that it moves like this relative to the shore? If you're saying to yourself, point it into the second quadrant like so, you're correct. And then ultimately we have the following. The velocity of the boat with respect to the water, plus the velocity of the water with respect to the shore. That then equals the velocity of the boat with respect to the shore. You just did v equals v prime plus u. Here's what the triangle looks like. Here's the velocity of the boat with respect to the water, v prime. Here's the velocity of the water with respect to the shore, u. That then gives us right here the velocity of the boat with respect to the shore. This right here is v, and then once again it's a right triangle. Now we know this side of the triangle is 2 meters per second. And now we know the hypotenuse of the triangle is 3 meters per second. So even though it's a right triangle, is it the same right triangle as what we had earlier in part A? No, it's not. Basically, two of the sides, if you will, have switched identities here in this example. So I'm going to once again use Pythagorean theorem here in just a few moments to find the speed v of the boat with respect to the shore. And then I'm going to use a little bit of trigonometry to find this angle right here. Call it phi, because this angle right here is going to be different than what we found earlier, the angle theta up on the top board for part A. But let's once again go ahead and use Pythagorean theorem here to find v. But notice that the Pythagorean theorem is written differently than what we have on the top board for part A. In this case, we have u squared plus v squared, v squared, there we go, is equal to v prime squared. And now we solve for v. So subtract the u squared to the other side like so, and then take the square root of both sides. Like so. So in this case, the speed of the boat with respect to the shore is going to be the square root of 3 squared, so 9 minus 2 squared. 9 minus 4 is 5. The answer is root 5. So the square root of 5 is about 2.2 or so meters per second. Okay, in this case, in order to find this angle phi, what I'm going to do is use a little bit of sine as opposed to tangent up on the top board. In this case, the sine of the angle phi is equal to the opposite side u divided by the hypotenuse v prime. So sine of phi is u over v prime. So then therefore the angle is the inverse sine of 2/3. So when I do inverse sine of 2/3, I end up with an angle of about 42 degrees, like so. Okay, now I actually have a screencast posted for you in today's folder. It's posted as an Ed puzzle, by the way. I have a screencast posted for you in today's folder of this problem. This screencast is called vector addition, or it's called vector addition, the velocity of a boat. So go ahead and pause the lecture here and go ahead and watch that screencast. That screencast is specific to this example here. Okay, now that you've seen that screencast, let's go ahead and move on to the next two-dimensional example here, once again forming a right triangle. This is another situation that you're familiar with, and it involves the rain. So for example, let's say that we have rain that is falling vertically at a constant speed relative to the ground. Now, if the rain is falling vertically at a constant speed, this means that there is air resistance involved. Once again, there are no accelerations. And then let's say that you get into a car and you drive into the rain. Have you ever noticed the following while it's raining? Have you ever said to yourself while you're driving in the car, wow, it's really raining hard? And then you stop and get out of the car and you say to yourself, well, it's actually not raining that hard at all. Why is it that you saw a difference in the rain while you were in the car as opposed to being out? Because you're seeing different velocity vectors. Okay, let's go ahead and access this next example. I need to erase my board and then move my file. Okay, so the problem is as follows. Okay, so reading the problem to you, rain is falling vertically at a constant speed of 8 meters per second as seen by a stationary observer. Once again, there's air resistance involved. The second observer is driving a car that is moving horizontally at a constant speed of 30 meters per second with respect to the ground. At what angle and with what speed does the observer in the car see the rain at? So that's what we're asked to solve for here in the example. Once again, we begin by identifying everything. First off, the stationary reference frame is the ground. Okay, and then what is the moving observer O prime and what is the object? Remember that the object is always the thing that is being described with respect to two other things. In this case, that's the rain. We're describing the velocity of the rain relative to the ground and relative to the car. This then means that the car is the moving reference frame O prime and the object is the rain. Like so. Okay, and now we're once again given two of the vectors and we have to find the third. So let's see if we could figure out which vector is which. Okay, first of all, it says that the rain is falling vertically at a constant speed of 8 meters per second as seen by a stationary observer. So that's describing the magnitude of the following velocity vector. It's describing the velocity of the object, the rain, relative to the ground, the stationary reference frame. So it's describing the magnitude of V. So the V vector, like so, points vertically like so with a magnitude of 8 meters per second. Okay, and then the moving observer, the second observer, is driving a car that is moving horizontally at a constant speed of 30 meters per second with respect to the ground. We'll say that that's to the right-hand side. That's describing the velocity of the car, the moving reference frame, relative to the ground, the stationary reference frame. So then therefore, that's the velocity vector U. Okay, now it does have a magnitude here of 30 meters per second. So I'll go ahead and draw it large as so. Okay, and then what we're asked to solve for here is V prime, the velocity of the rain relative to the car. How can you begin to picture what that vector has to look like? Well, draw upon your own experience. Let's say, for example, that the rain is falling vertically like so relative to the ground, but now you're in a car and you're driving in this direction like so through the rain. Relative to you inside of the car, in which direction roughly do you see the rain as falling? Well, you're going to see the velocity of the rain as something that looks like this, like so, relative to you inside the car. If you can picture that vector, we can now draw the vector triangle itself. It's a right triangle once again, and the vector triangle looks like this. V prime plus U is equal to V. So then therefore the velocity of the rain relative to the car plus the velocity of the car relative to the ground equals then the velocity of the rain relative to the ground. Once again, we're forming a right triangle here on the diagram like so. And then therefore, once we can picture the triangle, then we just need to use a little bit of basic trig to solve for the unknowns. Okay, so on this triangle, this side of the triangle is 8 meters per second. This side of the triangle is 30 meters per second. And then we'll use a little bit of Pythagorean theorem to find the speed of the rain relative to the car v prime. And then we'll once again use a little bit of tangent here in order to find this angle theta. As I've said, usually the hardest part of Galilean relativity is getting the triangle. Once you have the triangle, in this case a right triangle once again, then the math at this point is easy to solve for. All right, so let me do a little bit of erasing here, and then let's finish the example. So I'm going to go ahead and use some Pythagorean theorem here to find v prime. So u squared plus v squared is equal to v prime squared, and now I'll just plug in and take the square root. All right, so let's see. I'm going to have the square root here. First of all, u squared, so 30 squared is 900, and then plus v squared, so plus 8 squared, which is 64. Take the square root of all of that, and the speed of the rain relative to the car is a large number. It's about 31 meters per second. So if you've ever been in a car while driving through the rain and you've said to yourself, wow, it's really raining hard, well, it's because you're seeing the magnitude of a pretty large vector. However, if you stop and get out of the car, then you're only seeing the speed of the rain as 8 meters per second, and you may have said to yourself, well, it's not raining that hard after all. Once again, the reason for this is because you're seeing different velocity vectors. And then lastly, to complete the example, let's go ahead and use some inverse tangent here to find the angle theta. So the tangent of theta is equal to the opposite side of the triangle divided by the adjacent side of the triangle. That angle is going to be quite large in this case, by the way. It's the inverse tangent of 30 over 8. So dividing that out, and that comes out to be about a 75-degree angle, like so. The next time that it rains, assuming that it ever does again, the next time that it rains, you can actually see this problem in the following way. I usually demonstrate this later in the year if by chance during class, for example, it happens to be raining outside. What we do is we go outside to the balcony while it's raining, and then we just run down the hallway while looking at the rain. If you look at the rain while you're standing stationary, assuming that there's no wind, you see the rain falling vertically like so. But if you start running in this direction down the hallway, then you're going to see the v prime vector. You're going to see the rain very noticeably falling on a slant like so as you run down the hallway in this direction. I hope to be able to demonstrate that to you one day. Okay, I'm going to go ahead and pause the lecture here. This completes the examples involving two-dimensional cases with right triangles. For the last portion of the lecture, we'll take a look at situations involving non-right triangles.